Tonight we are going to do something that sounds harmless, but it can quietly rearrange your sense of reality. We are going to take the Milky Way, the thing that feels like the whole sky, and we're going to shrink it. Not by denying how huge it is, but by placing it next to the things that make huge look ordinary. The paradox is simple. Our galaxy is one of the bigger islands in the cosmic ocean, yet when you zoom out far enough it becomes almost nothing at all. Stay with me through the zoom. And if you like journeys that change your perspective, like this video and subscribe. Start with the most basic fact that almost nobody actually feels in their bones. The Milky Way is not a backdrop. It is a structure. A spinning disk of stars and gas and dust, with a swollen centre, wrapped in a halo of invisible mass that we only know is there because gravity will not stop confessing. If you could step outside and look at it from a safe distance, it would not feel like a gentle band of light. It would look like a luminous storm system. The Milky Way is roughly 100,000 light-years across. Say that slowly. 100,000 light-years. Light is the fastest thing we know. It does not crawl. It does not tire. It does not negotiate with distance. And even so, a beam of light would need about 100,000 years to cross from one edge of our galaxy to the other. When you hear numbers like that, your brain does its favourite trick. It nods politely and keeps living on the scale of streets and seasons, but that number is not decoration. It is the size of the home you're already inside. Now, pack that home with stars. Somewhere between 100 billion and 400 billion of them, depending on how you count what you cannot see well from the inside. That range is not astronomers being vague for fun. Counting stars from within a galaxy is like trying to count every tree in a forest while standing under the canopy at night. You can map the nearby trunks. You can estimate density. You can infer the hidden ones from the way light dims and dust blocks and gravity tugs. But you do not get a clean aerial photograph. You build the picture with patience and sometimes with humility. Our sun is one of those stars. It is not near the centre. It is not in the glamorous region where the star density climbs and the night sky would burn with too many points of light to name. We live about 26,000 light-years from the galactic centre, tucked into a minor spiral feature often called the Orion Spur. It is the suburbs, a calmer neighbourhood, fewer close stellar encounters, fewer violent events nearby. Enough time for a planet to cool, oceans to settle, life to start, and intelligence to arrive late to the party and ask what the party even is. And here is a quietly mind-bending fact that usually lands only if you stop and let it. Every star you can see with your naked eye on a clear night is part of the Milky Way. Every familiar constellation, every bright point you use as a guide, all inside this one structure. For most of human history that was the universe, not as a poetic guess, but as a sincere model of reality. The Milky Way felt like the edge of everything because it was the edge of what the eye could suggest. Then we learned the first betrayal of scale. The Milky Way is huge, yes, but most galaxies are smaller. That is the twist. When people imagine the universe, they picture titans everywhere, countless Milky Ways, all of them equally grand. But the typical galaxy is a dwarf, a faint collection of a few million to a few billion stars, small enough that if it lived in our neighbourhood, it might look like a supercluster even through a telescope. By that standard, the Milky Way is a heavyweight. It sits in the top slice, roughly the top few percent by size and mass, depending on the survey and the definition you use. In the cosmic census, we do not live in a random little runt, so if the Milky Way is big compared to most galaxies, why does it ever feel small? Because the universe is not organised around galaxies. Galaxies are not the top level of the story, they are chapters. The plot is written in larger structures. The first step outward is almost comforting. The Milky Way has neighbours. The closest major one is Andromeda, about 2.5 million light-years away. It is bigger in star count, often estimated around 1 trillion stars, and it is moving toward us. The numbers are dramatic, but the timescale is even more dramatic. A few billion years before the two galaxies fully merge. Your brain is allowed to exhale. This is not a disaster movie. It is a slow gravitational dance, with stars passing like ghost ships in an ocean so huge that direct collisions are rare. But the real reason Andromeda matters is not that it is coming. It is that it proves something. The Milky Way is not a lonely kingdom. It is a member of a group Around us is what astronomers call the local group, a small collection of galaxies spread across roughly 10 million light-years. The Milky Way and Andromeda are the dominant siblings. There is Triangulum, a smaller spiral. There are the large and small Magellanic Clouds, irregular companions you can see from the southern hemisphere as fuzzy patches, like the universe left fingerprints on the sky. And there are dozens of dwarf galaxies, many of them so faint we only discovered them recently, because modern surveys finally got sensitive enough to reveal the dimmest satellites hiding in the glare and dust. At this point, the Milky Way still feels important. We are one of the big two. We are the kind of galaxy that smaller galaxies orbit. That sounds like status. Then comes the shift in tension. The local group is not a big deal. It is huge compared to human life, yes, but it is a tiny neighborhood inside a much larger region of matter. Zoom out and you begin to see that groups of galaxies cluster into larger associations, and those into even larger ones, and eventually into patterns that look less like scattered islands and more like a web. A cosmic architecture built from gravity and time, and this is where the paradox starts to bite. You can be enormous and still be irrelevant. You can be in the top few percent and still be one speck among trillions. Both can be true because the universe offers you more than one scale to judge yourself by. So this is the promise of the journey. We are going to keep zooming, not to make the Milky Way feel worthless, but to make it feel true, to let you hold two opposing facts in your mind at the same time without flinching. The Milky Way is a cosmic giant compared to most galaxies, and the Milky Way is also the kind of thing that disappears when the real map comes into view. There is a strange handicap built into our situation. We are trying to understand the shape of the Milky Way while living inside it. That sounds normal until you realize how unfair it is. Imagine trying to map an entire city while you are locked in a single moving car, at night, in heavy fog. You can measure the speed of nearby traffic, you can count streetlights that break through the haze, but the skyline stays hidden and the city map has to be assembled from clues. That is the core problem of galactic astronomy. We do not get the luxury of stepping far away and taking a photograph. From Earth, the Milky Way is wrapped around the sky like a glowing river. Beautiful, yes, but beauty is not geometry. A band across the heavens does not tell you whether you live in a neat spiral, a messy spiral, a barred spiral, or something in between. And to make it worse, the Milky Way is not transparent. Between us and the center of the galaxy lies an enormous amount of dust and gas. In visible light, that dust is not a gentle haze. It is a wall. It blocks starlight the way smoke blocks a distant street lamp. So when you look toward the galactic center with your eyes, you're not seeing to the core. You are seeing a bright crowd in the foreground and then a dark lane where the light simply dies. This is why early maps of the galaxy were wildly incomplete. We could count stars in the directions that stayed clear, and we could guess the galaxy was larger in some directions than others. But any guess built on missing light is fragile. It is like trying to estimate the size of a forest while half of it is hidden behind a mountain. The breakthrough was not a single discovery. It was a slow expansion of our senses. Astronomers learned to stop relying on the narrow band of light our eyes evolved to notice. Dust that blocks visible light becomes far less stubborn in infrared light. So when we build infrared telescopes and point them toward the galactic plane, stars that were once erased by dust begin to reappear. The fog thins. The hidden skyline starts to outline itself. Radio observations push even farther. Gas clouds that are invisible to the eye can glow in radio wavelengths, and those clouds trace the skeleton of spiral arms. You can think of it like this. If stars are the lights of the city, gas is the road network and the construction zones, the places where new neighborhoods are still being built. Follow the gas and you begin to follow the structure. Now we hit the second handicap, distance. Knowing an object exists is not the same as knowing where it is. The sky is a dome of directions. A star can look close to another star but be vastly farther away. So to build a real map, we need depth. For nearby stars, there is a beautiful trick called parallax. As Earth moves around the Sun, a nearby star appears to shift slightly against the background of more distant stars. It is the same effect you see when you hold up a finger and switch which eye is open. That tiny shift, measured carefully, can be converted into distance. Parallax is not guesswork, it is geometry. But parallax has limits. The farther a star is, the smaller the apparent shift becomes, until it sinks below what our instruments can reliably detect. So astronomers built a ladder of methods. Some stars pulse in a predictable way, and the rhythm of their pulsing tells you how bright they truly are. Compare true brightness to apparent brightness and you get distance. For even larger distances, certain kinds of stellar explosions can act as distance markers, because their peak brightness follows a consistent pattern. All of this might sound like a collection of tricks, but it is really one idea repeated at different scales. If you can find something with a known property, you can use it as a yardstick. The cosmic distance ladder is not one magic tool. It is many tools stacked carefully, each one tested against the previous rung. In recent years, one of the most powerful advances has been the era of precision star mapping from space. Missions that measure stellar positions and motions with extreme accuracy can create a three-dimensional atlas of our local region of the Milky Way. When you have positions and you track motion over time, the galaxy stops being a painting and starts being a machine. You can see streams of stars that used to belong to smaller galaxies long ago, now stretched and blended into the Milky Way like ink in water. You can see the subtle drift of neighborhoods that are not fixed, but orbiting. This is where the emotional tone shifts. The Milky Way is not a static home, it is a dynamic system. Stars orbit the center, gas flows through spiral arms, new stars are born and old stars die, and the galaxy slowly reshapes itself over billions of years. Even our own sun is not sitting still. It is riding a long orbit around the galactic center, one lap taking hundreds of millions of years. And then there is the most frustrating part of all. The center of the galaxy, the place you would most want to see clearly, is the place most hidden by dust. We know a great deal about it anyway, not because we see it directly in visible light, but because we can watch stars whip around an invisible point with astonishing speed. When you see stars orbiting something you cannot see, gravity is pointing a finger. It is telling you mass is there, concentrated, compact, powerful. That is why astronomers conclude the Milky Way hosts a supermassive black hole at its core, commonly called Sagittarius A star. Notice what is happening in this story. We are not building our understanding from one kind of evidence. We are layering evidence. Star counts, infrared surveys, radio maps of gas, stellar motions, gravitational effects. Each method has its own blind spots, but together they lock the picture into place like overlapping pieces of a puzzle. The uncertainties remain, but they narrow. The map becomes less like a sketch and more like a measured structure. So when you hear that the Milky Way is about 100,000 light-years wide, that number is not a casual estimate. It is the outcome of decades of triangulation, inference, and cross-checks. It is the best answer we can build while trapped inside the thing we are measuring. And that is the weird beauty of it. We are made of material that evolved in this galaxy, on a planet inside this galaxy, and yet we can still infer the galaxy's shape with nothing but light, motion, and mathematics. We cannot step outside, so we turn the universe into a laboratory, and we let the Milky Way reveal itself through the ways it cannot help but behave. If the Milky Way is our city, then the next question is uncomfortable and personal. Where exactly do we live inside it, and why here? Not just because it looks nice on postcards, but because the galaxy is not uniformly safe. Some neighborhoods are crowded, some are violent, some are so quiet they feel empty. And if life needs time and stability and long stretches without catastrophe, then location is not a trivia fact. It is part of the plot. Picture the Milky Way as a rotating disk. Stars orbit the center. Gas swirls along with them. Spiral arms are not rigid spokes that hold still while everything rotates. They are more like traffic jams in a highway ring, regions where material bunches up, compresses, and triggers starbirth. They are beautiful, but they are also busy, and busy places tend to have consequences. Our Sun sits about 26,000 light-years from the galactic center, in a minor spiral feature called the Orion Spur. That detail matters because it suggests we are not deep inside one of the main dense spiral arms. We are close enough to the action to have access to heavy elements, the carbon and oxygen and iron needed for rocky planets and chemistry, but far enough from the worst crowding that long-term stability becomes possible. Now let us talk about what makes a galactic region dangerous, because this is where the romance of a star-filled sky meets the hard physics of living near explosions. In the inner regions of galaxies, closer to the center, stars are packed more tightly. In crowded stellar environments, close encounters become more common. Most stars still never hit each other. Space is too big even in a crowd, but gravitational nudges add up. A passing star can disturb the outer parts of a planetary system, jostle comets, stir up long-period orbits, and increase the chance of impacts. The galaxy does not need to throw a rock at you directly. It only needs to nudge your cosmic pantry shelves and let gravity do the rest over millions of years. Crowded regions also mean more massive stars, and more massive stars mean more violent endings. Massive stars live fast and die loud. Their deaths as supernovae flood nearby space with intense radiation and energetic particles. A supernova close enough is not just a pretty light show. It can damage atmospheres, alter chemistry, and stress a biosphere in ways that are hard to recover from. The Milky Way forms roughly 1 or 2 new stars each year, and among that steady creation are short-lived giants that will eventually explode. Where those giants are born matters. Then there is the center itself, the region we cannot even see in visible light because dust blocks it so effectively. We infer a supermassive black hole there because we can watch stars orbit something invisible with extreme speeds. Most of the time, that black hole is relatively quiet, but in other galaxies, central black holes can become active, feeding on infalling gas and blasting radiation outward. An active galactic nucleus can outshine the combined light of its galaxy. It can heat gas, disrupt star formation, and bathe surrounding regions in harsh energy. The Milky Way is not currently in that state, and we should be grateful, but the possibility exists in the broader story of galaxy evolution. So we have a list of hazards that are not movie monsters. They are slow statistical pressures, close encounters, impacts, radiation, crowding, and then there is a subtler hazard. The Milky Way is full of dust and gas clouds, and some of those clouds are the birthplaces of stars. Star-forming regions are stunning, but they are also turbulent. They generate strong stellar winds, hot young stars that emit ultraviolet radiation, and chaotic environments that can be rough on nearby planetary systems. Now pause and notice the tension that is building. The galaxy is not designed for life. It is not hostile on purpose, but it is full of energetic events that simply do not care whether a biosphere is trying to get established on some ordinary planet. Life, if it emerges, is a tenant. It survives at the mercy of its neighborhood. This is why our location starts to look less like an accident and more like a sweet spot. Not the center, not the far edge, not in the densest spiral arm, not completely isolated. Somewhere in the middle, in a relatively calm lane, where the galaxy's chaos is distant enough to be survivable but close enough to provide the elements that make complex chemistry possible. Even that sweet spot is not a permanent address, because the sun is moving. We orbit the galactic center. Over hundreds of millions of years, we complete a long loop, and along that loop we drift relative to spiral patterns. That means that over deep time, the solar system can pass closer to, or farther from, star-forming regions. It can experience periods where nearby supernovae are more likely, and periods where the neighborhood is calmer. The galaxy has seasons, not in temperature, but in risk. The sky above your planet is not just a view, it is a changing environment. The Milky Way also has a vertical thickness, and stars bob up and down through the disk as they orbit, like boats on a slow ocean swell. When you cross the mid-plane, you pass through denser regions of gas and dust. That can alter the gravitational environment slightly and change the frequency of interactions with clouds and debris. Again, no single crossing is a doom event. The point is that motion matters, and the timescales are huge. So when the original story says we live in a quiet neighborhood where supernova explosions are rare enough that life had a chance to develop, it is making a claim about probability. Our region is not a guarantee of safety. It is a reduction in the odds of catastrophe. Nature does not promise. It only leans. This is also why the Milky Way feels different once you truly accept it as a system. It is not a static shell of stars. It is a gravitational ecosystem. It produces stars, it destroys them, it mixes their ashes into new generations, and it drifts through larger structures that tug and reshape it over billions of years. We are inside a living machine made of time, motion, and physics, and here is the dramatic turn that sets up everything that comes next. Even if our local neighborhood is quiet, the Milky Way itself is not alone. The greatest dangers and the greatest changes may not come from within our own disk, but from the larger environment the entire galaxy swims through. We found a calm street inside a vast city. Now we need to ask what kind of country that city sits in. Now we meet the nearest reminder that galaxies do not live as lonely islands. Andromeda sits about 2.5 million light years away. That number already bends the mind, but the real bend comes from what it implies. If you can have a neighbour that far away and still call it nearby, then you are living on a scale where distance has new meanings. Andromeda is also big. It likely holds around 1 trillion stars, give or take, depending on where you draw its edges and how you count the faint outer regions. In many ways, it is the heavyweight of our local neighbourhood. If the Milky Way is a major city, Andromeda is the larger metro area down the coast, brighter, broader, and loaded with history. Here is the part that always gets turned into a headline. Andromeda is moving toward us. If you stop there, your imagination does what it always does. It grabs the nearest familiar pattern. Two objects collide. Collision means impact. Impact means destruction. Roll credits. But galaxies do not collide the way cars collide. They are not solid. They are mostly empty space with a sprinkling of stars and a haze of gas, all held in a shared gravitational embrace. When two galaxies meet, the thing that truly collides is their gravity. The stars, incredibly, usually pass by each other, like distant ships in a fog, rarely touching, rarely even coming close. This is where scale saves you from the Hollywood version. Inside a galaxy, the distance between stars is enormous compared to the size of the stars themselves. If the Sun were the size of a small coin, the nearest star would be many kilometers away. That means even when two galaxies overlap, most stars still never come near another star. They simply keep orbiting through a changing gravitational landscape, their paths gently bent and reshaped by the combined mass of everything around them. So when we say the Milky Way and Andromeda will collide, what we really mean is they will merge. They will approach, distort each other, pull out long tidal streams of stars, then swing past, then fall back, then swing again, over and over, until the two separate identities dissolve into one new system. It is a slow dance measured not in years, but in billions of years, and that time factor matters more than almost any other detail. The merger is expected on the order of 4.5 billion years from now. That is not next week. That is not next million years. That is a time horizon so deep it sits beyond the lifetime of our sun as we know it. Even if you could freeze your fear perfectly, it would not have time to stay fresh. But do not let the distance in time trick you into thinking it is irrelevant. The fact that this merger is coming tells you something fundamental about where we live. The local group is not just a collection of galaxies that happen to share a patch of sky. It is a gravitational family. And gravity always plays the long game. Even if the universe as a whole is expanding, gravity can bind a local region tightly enough that the members drift together instead of apart. The Milky Way and Andromeda are the clearest proof of that. They are not being carried away from each other by expansion. They are falling toward each other through the quiet tug of mass. This also explains why the merger is not a chaotic crash, but a slow reshaping. The gravitational pull acts across millions of light years and billions of years. It does not slam, it sculpts. What happens during a merger like this is fascinating because it reveals what galaxies really are. Not rigid objects, but patterns of motion. The familiar spiral arms can be ripped and zeered. The disks can thicken. The stars can be flung into long arcs that reach far into intergalactic space, only to fall back later like a tidal wave returning to shore. The most dramatic effects often happen to gas. Gas clouds can compress when galaxies interact. That compression can trigger bursts of star formation. In other words, a galaxy merger can be a creator as much as a destroyer. It can light up new generations of stars in brilliant waves. It can also funnel gas toward the center, potentially feeding the central black holes and making them more active for a time. The Milky Way is quiet now, but a major merger is the kind of event that can wake a galaxy up. So the future Milky Way is not just bigger, it is different. The final remnant is often expected to look less like a graceful spiral and more like a large elliptical galaxy, a rounded swarm of stars with less organized structure. Some people nickname this future system Milkdromeda. Others use Millimeda. The name is not the important part. The important part is what it represents. Galaxies evolve. They change identity. They do not stay in the shape you grew up imagining. And there is a strange emotional twist here. The merger is far too distant to threaten your daily life, but it is close enough in cosmic terms to remind you that nothing about our home is permanent. Even the Milky Way, which feels like a fixed ceiling of stars, is a temporary arrangement of matter passing through a temporary chapter of the universe. That is the real payoff of thinking about Andromeda. It is not fear, it is perspective. Because once you accept that our galaxy is already locked in a slow dance with a larger neighbour, you stop seeing the Milky Way as the final unit of importance. You start seeing it as one moving piece inside a bigger environment. The local group is a family with a future, and that future is written in gravity, which does not care about the stories we tell ourselves. Next, we take the step that really changes the feeling of the map. We leave the family living room and walk out into the wider region where thousands of galaxies gather, where the Milky Way is no longer a dominant sibling but one of many. The local group sounds like a casual phrase, like a club you join without thinking. But it is a real gravitational neighborhood, a small society of galaxies that share the same patch of cosmic space, and more importantly, the same slow set of gravitational negotiations. On paper, it is simple. The local group is a region roughly 10 million light-years across. Inside it are around 50 known galaxies, though that count keeps shifting as surveys get better at spotting the faintest members. Most of those galaxies are dwarfs, not the grand spirals that dominate posters and documentaries, but small dim systems that can carry only a tiny fraction of the stars found in a large galaxy. The local group is not a gathering of equals. It is a family where two large siblings take up most of the room. Those siblings are the Milky Way and Andromeda. They are the heavyweights. They hold the largest shares of mass. They host the largest systems of orbiting satellites. They define the motion of the smaller members simply by existing. In a sense, the local group is arranged around them the way a small town is arranged around two major cities. Everything else feels local, dependent, and slightly temporary. This matters because it reveals a trick that scale plays on your intuition. When you live inside the Milky Way, it is easy to imagine that our galaxy is the main event. Even after you learn there are other galaxies, it is still tempting to picture them as scattered extras, distant and decorative. The local group breaks that spell. It forces you to admit that the Milky Way is one major object inside a community, and that the community has structure, politics, and history. Take the large Magellanic Cloud and the small Magellanic Cloud. From the southern hemisphere, they are visible as faint, cloudy patches of light. For thousands of years, humans saw them and told stories about them without knowing what they were. Now we understand they are companion galaxies, irregular in shape, orbiting the Milky Way, carrying their own stars, gas, and internal drama. They are not mere ornaments, they are separate systems that happen to be caught in our gravity. And around those well-known companions, there is a whole swarm of far fainter satellites. Dozens of dwarf galaxies orbit the Milky Way. Many are so dim that they were only confirmed in the modern era, when wide sky surveys and careful analysis started to reveal the smallest stellar overdensities against the background of the Milky Way itself. Some of these dwarfs are so faint they feel almost like a philosophical question. At what point does a tiny group of stars stop being a galaxy and start being a star cluster? The answer depends on gravity. If the object behaves like it is held together by a significant dark matter halo, astronomers tend to treat it as a galaxy, even if it contains only a few thousand stars. The existence of these ultra-faint dwarfs tells you something important about the universe. It does not only build grand things, it builds countless small things, then it lets them orbit, merge, and sometimes disappear. Large galaxies do not simply exist. They grow, they feed slowly on smaller neighbours. The local group is a stage where that growth can be watched in real time, at least in geological time. The Milky Way is currently interacting with smaller galaxies. Stars are being pulled into long streams that wrap around the halo. Gas is being stripped, compressed, and relocated. These events are slow, but they leave signatures. If you map stellar motions and chemical fingerprints carefully enough, you can read the local group like an archaeological site. Past mergers become visible as ghostly trails. Now add the other side of the family. Andromeda has its own satellite system, its own dwarfs, its own history of swallowing smaller neighbours. The local group is not one galaxy with a few pets. It is two major galaxies with their own miniature ecosystems, separated by a distance that is enormous by human standards and yet intimate by cosmic standards. They are close enough to matter to each other. That brings us to a quiet emotional shift. Being a dominant galaxy inside a small group can feel impressive. It feels like status, but status is relative, and the universe loves reminding you of that. The local group, for all its vastness, is not a giant structure. It is not a rich cluster packed with thousands of galaxies. It is not a roaring metropolis of gravitational chaos. It is a modest neighborhood, relatively quiet, relatively sparse. The Milky Way is one of the largest members, yes, but the group itself is small enough that being second largest does not make you a ruler of the cosmos. It makes you a big fish in a small pond. And there is a deeper twist. The local group is not even a clean boundary. Its edges are fuzzy. Gravity does not draw sharp lines. Beyond the local group are other groups and galaxies that tug at the outskirts. Some objects sit in ambiguous territory, where it is not obvious which gravitational family they truly belong to. The universe is full of overlapping influences, like weather systems meeting over an ocean. So the local group is best understood not as a box, but as a region where gravity has managed to keep a set of galaxies loosely bound together, resisting the general expansion of space. That resistance is the key. It tells you where gravity wins locally, even as the universe expands globally. Now notice what this implies about our place. If we are inside a bound group, then we are not simply drifting alone through emptiness. We are part of a moving ensemble. Our galaxy's motion is shaped by nearby masses. Our future is partly determined by the trajectories of neighbours, and our sense of cosmic isolation changes shape. We are isolated from most of the universe, yes, but within our small neighbourhood, we are embedded in relationships. This is where the tension shifts again, because once you accept the local group as real and structured, you start to wonder what comes next. If groups are real, do groups gather into something larger? If the Milky Way and Andromeda are two siblings in a family, is the family part of a city? Is the city part of a nation? The answer is yes. And the next scale up is where the Milky Way stops feeling like a main character and starts feeling like a single line in a census. The local group is where the Milky Way still gets to feel important. Two big siblings, a swarm of smaller companions, and enough empty space between everyone that the neighbourhood feels quiet. But the universe does not stop at quiet neighbourhoods. It stacks neighbourhoods into cities. The next step up is where the map starts to sting. Astronomers use a few words that sound ordinary until you feel what they mean. A group is a small gathering of galaxies held together by gravity, like our local group. A cluster is a much larger gathering, hundreds or thousands of galaxies in a crowded gravitational hub. And a supercluster is what happens when clusters and groups gather into an even larger region, not necessarily a single tightly bound object, but a vast association that shares a broad flow through space. Our local group sits inside a larger region commonly linked to Virgo. The name comes from the Virgo cluster, the nearest rich cluster of galaxies and one of the first places where you really sense what crowded cosmic architecture looks like. The Virgo cluster lies tens of millions of light years away, and it contains something like 1,000 to 2,000 galaxies. Read that again and let it land. 1,000 to 2,000 galaxies, each with its own stars, planets, gas, dust and dark matter halo, all moving in a shared gravitational arena. Compared to that, the local group is a small household. This is the first true scale whiplash. Not because the Milky Way changes size, but because the room it sits in suddenly becomes enormous. Inside a rich cluster, the Milky Way is not one of two dominant siblings. It is just another spiral among many, one citizen in a packed city. Clusters are not just bigger, they are harsher. The space between galaxies inside a cluster is filled with extremely hot gas that shines in X-ray light. It is thin, far thinner than any vacuum we can make on Earth, yet it spans the entire cluster and carries tremendous energy. When a galaxy moves through this environment, that hot gas can push on the galaxy's own gas like a wind. Over long timescales, it can strip a galaxy of the very material needed to form new stars. It is one of the reasons many cluster galaxies look older and redder. Their star formation has slowed or stopped because their fuel has been stolen by the environment. And then there is the simple reality of crowding. In clusters, galaxies pass closer to each other more often. They tug, they distort, they trade stars and gas. Some merge, others get stretched into long streams, a galaxy that lives in a cluster is not living in peaceful isolation. It is living in a busy intersection. This is where the Milky Way's actual situation starts to look like a lucky accident. We are not inside the Virgo cluster. We are in a quieter region. We are close enough to belong to the broader neighbourhood, but far enough to avoid the worst of the crowd. That distance may have helped the Milky Way keep its gas and keep forming stars at a steady, modest pace for billions of years. A calm galaxy is not as flashy as a starburst galaxy, or an active nucleus blasting jets across space, but calm has its own power. Calm is time, and time is what life spends. Now here is the part that hits the ego. The Virgo cluster does not just contain many galaxies, it contains monsters. One famous example is Messier 87, a giant elliptical galaxy that dominates its local region of the cluster. It is not shaped like a delicate spiral disk. It is more like a massive swarm of old stars, the kind of galaxy that tends to form and grow in crowded environments by consuming smaller neighbours over billions of years. Messier 87 is also known for hosting an enormous central black hole, the kind of object that can shape the story of a galaxy's core. The important point is not the celebrity of a single galaxy. The important point is what that celebrity represents. In a rich cluster, the Milky Way is not a king, it is not even a major boss. It is a medium-sized spiral that would have to share the sky with many galaxies larger, brighter, and more massive. This is the first time the Milky Way starts to feel like a background character. And it is not because our galaxy is small, it is because the universe has contexts that dwarf even large galaxies. The local group is already a leap beyond the idea that the Milky Way is everything. The Virgo region is the next leap beyond the idea that the local group is a big deal. So when you imagine the Milky Way now, try holding two images at once. One image is home, 100,000 light-years wide, packed with hundreds of billions of stars, already too large for a human mind to truly inhabit. The other image is a single member of a vast crowd, one spiral among thousands, drift-folding in a broader sea of galaxies that are bound and shaped by forces far beyond our local comfort. The tension shift is subtle but permanent. We have not even reached the grandest structures yet, and already the Milky Way has lost its starring role. It is still home, it is still astonishing, but it is no longer central in any meaningful way. And that sets up the next step, because once you see that clusters and superclusters exist, you begin to wonder about motion. Not the motion of stars inside a galaxy, but the motion of entire galaxies and clusters through space. If the universe is expanding, why do we still see large-scale flows? Why does our region drift as if something is pulling on it? That question leads us into the strange idea that we are not just located in a structure, we are moving with it, sliding along an invisible landscape of mass we cannot fully see. Up to now, our zoom has been mostly about size. Bigger structures, bigger crowds, bigger contexts, but scale has another dimension that is even more unsettling than sheer width. Motion. Because the Milky Way is not just sitting in space like a museum exhibit, it is moving. And not only in the obvious way, orbiting its own centre. Our entire galaxy, along with our neighbours, is drifting through the universe in a coordinated way, as if we are caught in a current. That sounds impossible at first, because we are also told the universe is expanding. Galaxies are receding. Space is stretching. So why would there be a current at all? Shouldn't everything simply drift away from everything else, like dots painted on an inflating balloon? Here is the key idea. Expansion is real, but gravity is local and stubborn. Expansion sets the background trend. Gravity adds deviations, extra motions on top of that trend. Astronomers call these peculiar velocities, which is a polite way of saying the universe is not behaving as neatly as our first simple picture suggests. When astronomers measure how our galaxy and nearby galaxies move, they find a shared drift in a particular direction. The numbers are large, on the order of hundreds of kilometers per second. It is fast enough that if you take it seriously, it stops feeling like a mine of a correction and starts feeling like a clue. Something is pulling. Something massive is shaping the flow of our region of space. This is where the story becomes eerie, because the pull seems to come from a part of the sky that is hard to study. The direction lies near the plane of the Milky Way, where dust and gas block much of our view and visible light. It is like trying to investigate the landscape beyond a mountain range while standing in a valley filled with fog. You know something is there because you can see how the trees bend in the wind, but the source of the wind is hidden. So astronomers had to become detectives. They used wavelengths of light that can slip through dust more easily, like infrared. They used X-ray observations to find hot gas in clusters. They used radio surveys to map structures that visible light refuses to reveal. Over decades, a picture emerged of a dense region of galaxies and clusters in that general direction, including a prominent cluster often discussed in this context, the Norma cluster. The idea that formed around this was given a name that sounds almost mythic, the Great Attractor. It is not a single object you can point to and say, there it is. It is more like a region, a gravitational basin, a convergence area in the large-scale flow of galaxies. It is the place our local cosmic river seems to be heading toward, and it becomes even stranger when you realize this region is not the whole story, because the deeper you look, the more the map reveals that the pull may be influenced by even larger mass concentrations farther away. One of the big suspects in that larger story is the Shapley supercluster, an enormous concentration of galaxies located hundreds of millions of light years away. The logic is simple. If you gather enough of the mass in one region, it will shape the motion of everything around it, even at huge distances. The trouble is that the universe is messy. Mass is distributed in a web, not in a neat set of isolated blobs. So the flow we measure is likely the result of multiple structures pulling at once, overlapping influences creating a combined direction, like tides shaped by more than one moon. Now take a breath and notice what just happened. We started with a galaxy, we zoomed to a group, then to a cluster environment, and now we're talking about flows of galaxies across enormous volumes. At this scale, the question is no longer just where we are. The question is, what basin of gravity do we belong to? This is where the concept of laniakea enters the story. In the last decade, astronomers proposed a way to define a supercluster not merely by where galaxies are located, but by how they move. Instead of drawing a boundary around a dense region and calling it a supercluster, they traced the flow lines, the directions galaxies drift under gravity. They looked for basins where motions converge, where the cosmic river seems to drain. By that definition, the Milky Way is part of a vast region often called Laniakea, a name that roughly translates to immeasurable heaven. Whether you treat Laniakea as a sharp physical object or as a useful way to describe a flow basin, the emotional impact is the same. It tells you that we are not just near Virgo, we are not just near a cluster. We are inside a much larger gravitational landscape, one that includes many groups and clusters spread across hundreds of millions of light years. And inside that landscape, our local group is not steering the ship. It is cargo. This is the moment where scale stops being a simple ladder of sizes and becomes something more like weather. Galaxies move the way leaves move in a river. They have their own internal motions, their own spins and tides and histories. But when you zoom out far enough, they also participate in vast collective flows shaped by hidden terrain. The terrain here is the distribution of mass, visible and invisible. The riverbed is dark matter scaffolding. The currents are gravity acting over time, and it is not just poetic language. If you map enough galaxies and measure their motions well enough, you can literally draw streamlines. You can watch how matter drains toward one region and away from another. You begin to see that what looks like an empty patch of space is often the edge of a gravitational valley. So the Great Attractor is not a monster, it is a symptom. It is what you call it when the local universe stops looking random and starts looking like a flow field. It is what you call it when you realize that even your galaxy, which once felt like the whole stage, is being carried by forces that do not care about your personal sense of center. The tension shift here is profound because it changes what it means to be located somewhere. We are not just positioned in the Milky Way. We are in the Milky Way, which is in the local group, which is in a larger region, which is part of a vast basin of attraction, which itself is one pattern in an even larger web. We are nested inside motion. And now the next question becomes unavoidable. If gravity shapes flows and if flows reveal basins, then what does the entire universe look like when you stop thinking of it as scattered dots and start thinking of it as structure? That takes us to the cosmic web itself, where the real architecture is not the bright galaxies, but the empty spaces between them. When most people imagine the universe, they imagine dots, galaxies sprinkled through space like glitter thrown at random. It is a comforting picture because it matches what the sky looks like at first glance. A scatter of lights, a black background, end of story. But the universe is not a scatter. It is a structure. The moment astronomers started mapping galaxies in 3 dimensions, measuring not only where they appear on the sky, but how far away they are, the dots stopped behaving like dots. They began to line up. They formed threads, sheets, knots, and long arcs. The universe revealed a hidden architecture, and the name that stuck is almost too perfect: the cosmic web. Think of it as the largest kind of pattern gravity knows how to draw. Over billions of years, matter falls inward, where it is slightly denser, and it drains away from places that are slightly less dense. Dense regions grow denser, sparse regions become emptier. The result is a universe that looks like a network, a tangle of filaments connecting denser nodes surrounding vast hollows. And those hollows are the part that changes your emotional relationship to space, because the cosmic web is not just a story about where galaxies are. It is also a story about where galaxies are not. The web is wrapped around enormous voids, regions where the density of galaxies is dramatically lower than average. Not perfectly empty, not a true nothingness, but empty enough that if you lived there, the universe would feel lonely in a way that is hard to put into words. Voids are not small gaps. Some span hundreds of millions of light years. Some stretch even farther. They can be so large that the Milky Way, which already feels gigantic, becomes a tiny motif you could stamp across the void thousands of times and still not fill it. One well-known example in the nearby universe is a vast underdense region often discussed as the Keenan-Barger-Cowie void, named after the researchers who studied it in detail. It is described as being on the order of billions of light years across. Let that phrase land. Billions of light years. A region so wide that light would spend longer crossing it than complex life has existed on Earth. Now imagine, not as a math problem but as a lived scene, that you are transported to somewhere near the middle of such a void. You look out in all directions. There is no nearby wall of galaxies, no dense cluster, no obvious cosmic skyline. The nearest major gatherings of galaxies could be hundreds of millions or even about 1 billion light years away, depending on where exactly you are in the void. At those distances, even large galaxies do not look like swirling masterpieces. They look like faint smudges, tiny pale hints that anything exists at all. The void would feel like deep ocean at night, not because there is literally nothing, but because the distances between interesting things become so large that your intuition stops working. The sense of neighborhood collapses. Everything becomes far, everything becomes slow, and here is the twist that makes voids more than just emptiness. Voids are not a side effect, they are a defining feature. By volume, most of the universe is closer to void than to filament. Matter is clumped into a relatively small fraction of space, and the rest is stretched, thin, and quiet. The bright parts of the universe are the exception. The darkness is the default. This is one reason the scale of the universe feels so isolating. Even if there are trillions of galaxies in the observable universe, they do not fill space the way raindrops fill a window. They gather into webs and leave enormous regions in between. The universe is not crowded, it is structured, and that structure includes vast loneliness as one of its primary ingredients. Now bring our story back to the Milky Way. We have spent time treating our galaxy like a big object because it is. But within the cosmic web, a single galaxy is not the unit that matters. The unit that matters is the filament, a long thread of mass, mostly dark matter, that runs across space and collects gas and galaxies like dew forming along a spider's silk. Our local group sits on one of these threads. It is part of a larger flow, part of a broader basin, but structurally it is like a bead on a string. Nearby strings connect to other strings. Some strings thicken into walls or sheets. Where multiple filaments meet, you get nodes, and nodes are where clusters form, dense knots of galaxies held together by a deep gravitational well. If you want a mental picture, imagine the universe as foam. The filaments are the edges of bubbles, and the nodes are where many edges meet. The voids are the interiors of the bubbles. The foam is not static, it is frozen motion, the result of gravity amplifying tiny differences over enormous time. This also tells you something unsettling about what you're actually seeing when you look at a beautiful image of the cosmos. In many deep images, galaxies look evenly scattered across the frame. But that is a projection. It is a two-dimensional slice of a three-dimensional network. The true pattern only appears when you add distance, when you turn the sky into space. And once you do that, the Milky Way begins to feel like a local campfire in a continent-sized wilderness. Warm, bright, meaningful, but surrounded by distances so enormous that even the next campfire is unimaginably far. Voids also change how you think about what is important. When you hear about clusters and superclusters, it is tempting to treat them as the big story, the places where matter gathers and galaxies collide and black holes feast. But voids are not passive. They shape the web by being the places matter has drained away from. They define the boundaries. They are the negative space that makes the structure legible. They also tell us something about the past. Early in the universe, matter was spread more evenly. Tiny fluctuations existed, but the contrast between dense and empty was far smaller. Over billions of years, gravity sharpened the contrast, draining matter into filaments and leaving voids behind. So every void is a fossil. Not a fossil of a creature, but a fossil of an ancient distribution, a record of how the universe grew its structure. And here is the emotional punchline. If you are trying to understand the scale of the Milky Way, voids force you to accept a strange duality. Our galaxy is vast enough to contain hundreds of billions of stars. It is enormous by the standard of most galaxies, but it sits inside a web where emptiness dominates, where the most common experience of space is not crowded brilliance but extended quiet. That quiet is not just background, it is the stage. So the cosmic web is not merely a pretty concept, as it is the reason the universe looks the way it does at the largest scales, and it is the reason your home galaxy, for all its scales, can still feel like a flicker in a vast dark architecture. Next, we are going to see what happens when astronomers first proved that this architecture includes walls, gigantic sheets of galaxies that were hiding in plain sight until we learned to measure depth. That discovery is where the universe stops looking like a starfield and starts looking like a blueprint. There is a special kind of shock that only happens when you realize the universe was hiding something enormous in plain sight. Not because the galaxies were invisible. Many of them had been photographed for decades. The shock is that the pattern they form was invisible to us because our eyes and our instincts are both trapped in 2 dimensions. When you look at the night sky, you see a dome. Left and right, up and down, bright points and faint smudges. Everything looks like it is painted on the inside of a sphere. That view is honest, but it is incomplete. It tells you where things appear, not where they are. So for a long time, even after we learned galaxies were separate island universes, we still did not truly know how they were arranged in space. We had a map of directions. We did not yet have a map of depth. Depth is where the universe changes personality. To add depth, astronomers needed a way to estimate how far away a galaxy is, not just by guessing its brightness, but by using a physical clue carried by the light itself. That clue is redshift, the stretching of a galaxy's light toward redder wavelengths as space expands between us and it. For relatively nearby galaxies, redshift can be used as a rough distance indicator. The details are complicated because galaxies also have their own local motions on top of expansion. But as you gather large samples, the pattern starts to emerge. And once you gather large samples, the universe stops looking random. In the late 20th century, astronomers built surveys that measured redshifts for thousands of galaxies. These were not glamorous telescope posters, they were data projects, catalogues, rows of coordinates and numbers, the kind of work that looks boring right up until it changes reality. One of the early jolts came from the Center for Astrophysics redshift surveys, which revealed a gigantic sheet-like structure now commonly called the CFA Great Wall. It stretches across a region hundreds of millions of light-years in extent, with a thickness far smaller than its length and width. That is the key. It is not a ball, it is not a neat cluster, it is a wall, a membrane of galaxies. The discovery was a message. Galaxies are not only arranged in clusters, they are also arranged in sheets and filaments that can run across astonishing distances. But the even bigger jolt came later, when larger surveys expanded the sample size dramatically. The Sloan Digital Sky Survey did something simple and revolutionary. It mapped huge swathes of the sky and measured redshifts for an enormous number of galaxies. When you plot those galaxies in 3 dimensions, you do not get a glitter cloud. You get structure, dense strands, empty voids, and in that pattern, astronomers identified a structure that became famous as the Sloan Great Wall, stretching on the order of more than 1 billion light-years across. Try to feel that scale, not as a number, but as a comparison. 1 billion light-years is 10,000 times the diameter of the Milky Way. If the Milky Way were reduced to a single grain in your hand, a structure like this wall would be something you would need to lay out across a field to represent. And here is the eerie part. The galaxies that make up these walls are not glued together like bricks in a building. They are separated by enormous distances. Yet collectively, they trace a coherent feature in the cosmic web, a sheet where matter is denser than average, where gravity has guided the flow of galaxies and gas into a shared region. So why were these walls unknown for so long? Because a wall can look like nothing when you only see it as a projection. If you take a sheet of points and view it face on, it can appear as a simple cluster of dots. If you view it edge on, it can vanish into a thin line. The sky does not give you the viewing angle you want. It gives you only the angle you have. Without distance data, you are looking at a shadow of a three-dimensional object and trying to guess what cast it. That is why depth mapping was the turning point. The universe did not suddenly grow new structures. We suddenly grew new eyes. Once those eyes opened, the cosmic web stopped being a metaphor and became a measured thing. You could see how walls and filaments wrap around voids like the edges of bubbles. You could see how clusters sit at intersections. You could see how our own region is not isolated, but connected by threads of matter to larger patterns. And then the story gains a new kind of tension, because walls raise a dangerous question. Is there a limit to how big structures can be? Cosmology, our best large-scale model of the universe, predicts that beyond a certain scale, the universe should become statistically smooth, not perfectly uniform, but uniform in the sense that the largest patterns should not keep growing without bound. The early universe had tiny density variations. Gravity amplified them. But there is only so much time and only so much causal connection for matter to organize itself into coherent features. So when we find walls that stretch for hundreds of millions or more than 1 billion light-years, the obvious reaction is awe. The next reaction is suspicion. Are we seeing a single connected structure? Or are we seeing a chain of related features that our pattern-hungry minds are grouping into one name? Are we seeing the universe, or are we seeing our own desire for neat shapes? That tension is not a flaw in the story, it is the story. Because this is how science behaves at the edge of scale. We build bigger maps, we notice bigger patterns, and then we have to ask whether the patterns are truly physical objects or statistical features of a web. But either way, the emotional consequence for the Milky Way is the same. When you place our galaxy against a wall of galaxies, the Milky Way stops feeling like a vast city and starts feeling like a single porch light on one street of a continent's spanning grid. Still real, still precious, still home, but no longer the frame. And this sets up the next leap, the one that makes cosmologists shift in their seats. Because some claim structures are described as stretching far beyond what our tidy models would like. If those claims are robust, they hint that our understanding of the universe's largest scales may still be missing something. At some point in this zoom, the universe stops feeling big and starts feeling suspicious. Not suspicious in a conspiracy sense. Suspicious in a scientific sense. The kind of suspicion that makes you sit forward and ask whether your map is lying to you, or whether your theory is too neat for the real world. Because once you accept walls like the Sloan Great Wall, the next question is inevitable. How big can these structures get before the very idea of a single connected feature stops making sense? This is where the story takes us to the edge of what we can confidently claim and into a region where astronomers argue like responsible adults, loudly, with data. One of the most famous examples is a reported structure known as the Hercules Corona Borealis Great Wall. In some studies, it is described as stretching across an almost absurd span on the order of 10 billion light-years. If you hear that number and your brain tries to reject it, that is a healthy response. 10 billion light-years is not just larger than the Milky Way. It is a significant fraction of the age of the universe expressed as a distance, the kind of scale where you start wondering how anything could be organized at all. If a feature like that were truly one coherent structure, it would be a cosmic event in itself. It would mean that the web has strands so long and so pronounced that they challenge our expectation that the universe becomes smoother when you step back far enough. And that expectation is not arbitrary. It comes from the way modern cosmology describes the universe. Early on, matter was distributed almost evenly, with only tiny fluctuations. Over time, gravity amplified those fluctuations. Dense regions grew denser, sparse regions emptied out, and the cosmic web emerged. But there is a catch built into the physics. Information cannot travel infinitely fast. Gravity does not reorganize the universe in an instant. Structures need time to grow, and they grow within a universe that is expanding. At very large scales, the expectation is that the universe should become statistically uniform, meaning that while you still see filaments and voids, the extremes should fade, and no single feature should dominate a map across enormous fractions of the observable cosmos. In the original transcript, this tension is described in a sharp way. Some simulations suggested that the largest coherent structures should not exceed about 1.2 billion light-years. Then you place that next to a claim of about 10 billion light-years, and you get the uncomfortable question. Is our model wrong? Is our map wrong, or are we using the word structure too casually at the edge of our measurements? This is where things get subtle, and this is where the debate lives. At extreme distances, we do not map the universe the same way we map the local group. We are not measuring individual galaxy motions with exquisite precision. We are working with limited samples, selection effects, and surveys that see some kinds of objects better than others. Sometimes the structure being discussed is not a wall of galaxies you can point to directly, but a pattern inferred from a set of bright markers, like gamma-ray bursts, or from clustering statistics across a slice of sky. Patterns can be real and still be tricky. A chain of dense regions can look like one wall if you connect the dots. A coincidence can look like a feature if your sample is small. A real feature can look bigger than it is if your map stretches distances imperfectly. And the universe itself can produce startling runs of density without violating the deeper rule of statistical uniformity, the way a coin can flip heads 10 times in a row without changing the fact that the coin is fair. So when you hear a phrase like largest known structure, the healthy response is not blind belief or automatic dismissal. The healthy response is a calm question. What exactly is being measured? What exactly counts as connected? How strong is the statistical evidence? How does the result change if you use a different catalogue, a different tracer, a different method of defining the boundary? This does not drain the wonder out of the story. It actually deepens it, because it reveals something important about the frontier of science. The frontier is not a list of facts. It is a zone where facts are still being negotiated. And here is the emotional truth that holds even while the debate continues. Whether the Hercules Corona Borealis Great Ball is exactly as large as some reports suggest, or whether it is smaller, or whether it is a chain of features that our naming has fused into one, the cosmic web is still vast beyond normal intuition. Even the well-accepted walls and filaments already make the Milky Way feel like a single bead in a network too large to visualize cleanly. So the real takeaway of this part is not a single number. The takeaway is the tension itself. Our best models say the universe should smooth out at the largest scales. Our best maps keep showing striking patterns that tempt us to call them superstructures. Sometimes the patterns hold up and become part of the standard picture. Sometimes they soften as data improves, turning out to be less dramatic than early surveys suggested. And sometimes they remain genuinely strange, forcing theorists to revisit assumptions they thought were settled. This is what makes the universe feel alive as an idea. It is not finished. We are still learning what the biggest things even are. And notice what happens to our original paradox as we stand at this edge. The Milky Way is large enough to be a giant among galaxies. But at the scale where we argue about billion light-year walls, even giants become tiny. Next, we return to a different kind of scale comparison. Not bigger structures, but bigger and smaller galaxies. Because to truly understand where the Milky Way sits, we need to stop being hypnotized by the biggest claims and look at the full population, from ultra-faint dwarfs to the rare monsters that make headlines. After you have stared at walls, voids, and great flow basins, it is easy to forget a simpler truth. The Milky Way is not only small compared to the universe, it is also huge compared to most galaxies. Both are true, and the only way to hold them at once is to stop thinking in extremes and look at the full population. Most galaxies are not majestic spirals with sweeping arms. Most galaxies are dwarfs, small, faint, easy to miss, and vastly more common than the giants. Some dwarfs have a few billion stars, many have far fewer. Some are so dim they were discovered only recently, hiding as subtle overdensities of stars in wide surveys. These tiny galaxies are not rare curiosities. They are the main demographic of the cosmos. This is why the Milky Way's size is such a strange psychological trap. We grew up with a sky full of stars and a poetic band of light, so our home feels normal. But by galaxy standards, our home is not the default setting. A galaxy about 100,000 light-years across, with hundreds of billions of stars, is a heavyweight compared to the typical faint dwarf you would get if you picked a random galaxy out of the universe. The phrase that matters is not that we are the biggest. We are not. The phrase that matters is that we are in the upper slice. Surveys of galaxy populations find that the majority are smaller than the Milky Way by a wide margin. So when you hear that our galaxy is in something like the top few percent by size or mass, it is not bragging. It is a statistical description of where we sit in the distribution. And this is where the story turns into a cosmic zoo, because galaxies do not come in one neat size class. They come in a spectrum shaped by history. Some galaxies are compact and intense, with stars packed tightly and little gas left for future star formation. Some are diffuse, with stars spread out so thinly that the galaxy can be enormous in diameter and still be hard to see because the light is smeared across a vast area. Some are battered and irregular, distorted by interaction, carrying tidal tails like scars. The Milky Way is a spiral galaxy, with a disk and spiral arms, still forming stars at a modest pace. That alone puts it in a category that feels familiar to us, because spirals are the galaxies people tend to recognize. But spirals themselves range widely in size. There are spirals much smaller than ours, and there are rare giant spirals with disks extending far beyond the Milky Way's reach. One famous example often discussed is Malin 1, a giant low-surface brightness spiral. Its disk can extend to several 100,000 light-years depending on how you define its faint outer edge. The important point is not the exact number. The point is the kind of galaxy it represents. A system that is very large but very faint, so it hides in plain sight unless your surveys are sensitive enough. Then there are the giant elliptical galaxies, the heavy kings of crowded neighborhoods like rich clusters. These are the galaxies that often win the mass game, not because they were born huge, but because they grew huge by merging and absorbing other galaxies over billions of years. If the Milky Way is a well-organized city with active construction, a giant elliptical is more like an ancient capital that has swallowed surrounding towns until it became an empire of old stars. Some of these cluster-centered galaxies are so enormous that their faint outer halos blur into the surrounding intra-cluster light, making the idea of a clean edge almost meaningless. One widely cited example is IC 1101, associated with the Abell 2029 cluster. Depending on how you measure its extended halo, reported sizes can reach into the millions of light-years. That is not a simple comparison to the Milky Way's disk. It is more like comparing a bright downtown to an entire metropolitan glow that fades gradually into darkness. And that detail matters because it keeps us honest. When you compare galaxy sizes, you have to ask what you mean by size. The bright stellar disk, the faint outskirts, the dark matter halo which extends far beyond the visible stars. Galaxies are not hard-edged objects, they are gradients. So yes, there are monsters out there that can dwarf the Milky Way, but here is the trap. Those monsters are rare. The universe is not dominated by these extreme giants. It is dominated by dwarfs. The giants are attention magnets, not population averages. They are the outliers that teach us what is possible, while the dwarfs teach us what is common. This is why the Milky Way occupies such an odd emotional position in the story of scale. If you compare us to the rarest giants, we shrink. If you compare us to the typical galaxy, we loom. And that duality is not just a philosophical trick. It has consequences. A galaxy like the Milky Way tends to have enough mass to hold on to gas over long timescales, enough star formation to keep generating heavy elements, enough gravitational stability to build complex planetary systems, and enough time to let biology experiment. A tiny dwarf galaxy, by contrast, may struggle to hold its gas against stellar winds and supernova blasts. It can be stripped by interactions with larger galaxies, It can be chemically simpler, with fewer heavy elements, which matters if you care about rocky planets and complex chemistry. So when we say the Milky Way is large, we're also saying it is the kind of galaxy that can host a long, rich internal history. A history with many generations of stars, many rounds of element making, many chances for planets like ours to appear. Now let the tension shift again, because this is where the paradox sharpens. Even if the Milky Way is a heavyweight compared to most galaxies, it is still only one galaxy, one system, one island. And when you zoom out to the scale of the observable universe, you're not comparing us to a handful of neighbours. You're comparing us to a population that may number in the trillions. So the next step is to stop thinking only about individual galaxies and start thinking about the total count, the sheer multiplication of islands. That is where the Milky Way's size advantage stops mattering, and the true loneliness and immensity of the universe starts to bite. Once you have looked at dwarfs, giants, walls and voids, there is one move that still has the power to reset your internal compass. It is not a move to a bigger cluster or a bigger wall, it is a move to a bigger count. How many galaxies are we even talking about? Because it is one thing to say the Milky Way is large, it is another thing to place it into a universe that contains not thousands, not millions, but on the order of trillions of galaxies in the part we can observe. That number is not a poetic exaggeration. It is a scientific estimate built from deep surveys and statistical corrections for what we cannot easily see. A huge fraction of galaxies are faint. Many are small, many are far. So the farther you look, the more you miss unless your instruments are sensitive enough. Astronomers count what they can detect in deep fields, then use models and corrections to estimate what is likely hiding below the detection limit. The exact number is not a fixed inventory you can print on a poster, but the scale is clear. The observable universe contains an almost absurd abundance of islands. Now we need to define the phrase observable universe, because it sounds like a simple boundary and it is not. The observable universe is not the whole universe. It is the part of the universe from which light has had time to reach us since the beginning of the cosmic expansion we call the Big Bang. That is a very specific limitation. It is not about what exists. It is about what can be seen. In principle, by any observer here and now, the universe is about 13.8 billion years old. That number tempts your brain into a naive picture. If light travels 1 light year per year, then surely we can see out to about 13.8 billion light years in every direction. That would suggest a visible sphere about twice that across. But the universe refuses to be that simple. Space itself has been expanding the entire time. While a photon is travelling toward us, the space it passes through is stretching. The source that emitted the light is not sitting still in a fixed stage. The stage is growing. So the distance to that source today can be far larger than the simple light travel time would suggest. This is why you will often hear that the observable universe is about 93 billion light years across. That is not a contradiction of the universe's age. It is a consequence of expansion. Light can take 13 billion years to reach us, while the distance between us and the place it came from grows during the journey. The photon is like a swimmer crossing a river that is widening as they swim. The swimmer still reaches the shore, but the shore ends up farther away than it was when the swimmer began. That number, 93 billion light years across, is a kind of translation. It turns the history of expansion into a present-day scale. It is a statement about the size of our current observable bubble. Now pause and let that sink in with the Milky Way in your mind. The Milky Way is about 100,000 light years across. The observable universe is about 93 billion light years across. Even without doing any arithmetic out loud, you can feel the gap. Our galaxy is enormous, and yet it is a microscopic feature inside our visible bubble. And inside that bubble, there may be on the order of trillions of galaxies. This is where your intuition starts to fail in a predictable way. When numbers get too large, they stop feeling different. A million and a billion both become a lot. A billion and a trillion both become impossible. So we reach for metaphors. One metaphor is to imagine compressing each galaxy into something small, like a grain of sand. If every galaxy were a single grain, you would need an almost comical amount of sand to represent the observable universe. You are no longer talking about a handful in your palm. You're talking about containers, pools, stadium-scale volumes. The point of the metaphor is not its exact conversion. The point is the emotional truth. There are so many galaxies that the Milky Way is not visually special at that scale. It becomes one grain among an ocean of grains. And here is the next twist. Even this enormous observable bubble may not be the whole story. There is no evidence that the universe ends at the edge of what we can see. The observable boundary is not a physical wall, it is a horizon. It is the limit set by time and light speed and expansion. Beyond it, there could be more galaxies, more walls, more voids, continuing outward in every direction. We cannot see them not because they are not there, but because their light has not reached us, and depending on how expansion behaves, may never reach us. This is where the story gets almost philosophical, but it is still physics. If the universe is finite, it could still be far larger than the observable region. If the universe is infinite, then the observable region is not a small percentage. It is not a tiny percentage. It is effectively nothing compared to infinity. It is a bubble in an endless ocean. And even if you do not like the word infinite, even if you keep your feet on the ground of what we can test, you still face the same emotional consequence. We live inside a limited window. The universe may be vastly bigger than our window, and we may never know how much bigger. So what does that do to our original question about the Milky Way's true scale? It forces a second paradox to sit beside the first. Paradox 1 is that the Milky Way is huge compared to most galaxies, yet small compared to the largest structures. Paradox 2 is that even the largest structures we can observe may be only a small part of what exists. Now bring that back to the human scale, because this is where the tension becomes personal. When you hear trillions of galaxies, your mind almost automatically asks about life. With so many stars, so many planets, so many chances, why does the sky feel so silent? Why do we not see obvious signs of other civilizations? Why do we not hear a chorus of signals? The scale that makes the universe feel rich also makes it feel lonely. The same distances that allow trillions of galaxies also isolate them. A signal from the other side of the Milky Way would take tens of thousands of years to reach us. A signal from Andromeda would take millions of years. Across the wider universe, the numbers become so huge that contact starts to look less like a question of technology and more like a question of time, patience, and luck. And that is where we go next, because the Milky Way's size is not just a geometry lesson, it is also a lesson in isolation. The universe can be full and still feel empty because separation is part of the design. Trillions of galaxies, hundreds of billions of stars in our own, planets everywhere. At first glance, that sounds like a promise, a cosmic guarantee that life should be common and intelligent life should be inevitable. And yet, when we listen, the universe answers with static. This is not a new discomfort. It has a name, the Fermi paradox, the famous mismatch between what the numbers seem to suggest and what we actually observe. If the cosmos has so many places to live, where is everybody? But notice something important. The Fermi paradox is not only a question about biology and technology, it is also a question about scale. In fact, scale might be the quiet villain in the story, because the same enormity that produces countless opportunities for life also produces distances that can make those opportunities effectively unreachable. Start with the Milky Way itself, 100,000 light-years across. That means a message travelling at the speed of light would take 100,000 years to cross our galaxy. Not to cross the universe. Just to cross home, a civilization on the far side of the Milky Way could broadcast a powerful signal, and by the time it reached us, the culture that sent it might have changed beyond recognition or vanished entirely. We would be receiving a ghost, and that is just within a single galaxy. Now expand your imagination to the local group. Andromeda is about 2.5 million light-years away. A signal travelling at light speed would take 2.5 million years to arrive. That is longer than the entire history of our species. If we send a greeting today, the first reply arrives in a future so distant that our languages, our politics, and perhaps our biology might be different. Now expand again to the broader universe. Most galaxies are not 2.5 million light-years away. They are hundreds of millions or billions of light-years away. Those are not communication delays. Those are geological eras. Those are deep time. So even if intelligent civilizations are common, scale can turn a crowded universe into a set of isolated bubbles that never meaningfully interact. It gets worse. The universe is expanding. That expansion means distant galaxies are not merely far, they are becoming farther. There is a horizon effect. Beyond a certain distance, the rate at which space expands can carry objects away from us faster than light can traverse the growing gap. That does not violate the rule that nothing can move through space faster than light. It is space itself that is stretching. The consequence is brutal. There are parts of the universe we can see now, whose light is reaching us, but whose future light may never reach us again. They are slipping beyond causal contact. This transforms the question, where is everybody, into a more careful question. Even if everybody is out there, are we capable of ever knowing? And inside our own galaxy, there are additional filters that scale imposes. Signals weaken with distance, not linearly. They spread out. Even a powerful broadcast becomes a whisper when it has expanded across thousands of light years. To detect it, you need to be listening at the right time, in the right frequency range, with the right sensitivity, and you need the sender to be aiming or broadcasting in a way that is not purely local. Now, add the reality that technology changes. On Earth, we have been a radio-loud civilization for barely more than a century. That is nothing on cosmic timescales. It is a blink. Our strongest broadcasts into space are a thin shell expanding outward at the speed of light, currently about a bit more than 100 light-years in radius. Compared to the Milky Way, that shell is a tiny bubble inside a vast disk. So if another civilization exists elsewhere in the galaxy, there is a decent chance they have not even had time to notice us yet. And even if they did, there is no guarantee they would respond in a way we could understand or detect. This is why scale makes the silence less shocking. The universe can host life and still feel empty to any one observer, because the distances and times are so large that contact becomes the rare event, not the default. Now, that does not solve the Fermi paradox. It only softens one edge of it. There are still deeper possibilities. Maybe life is rarer than our simple arithmetic suggests. Maybe the jump from chemistry to biology is extremely difficult. Maybe complex life is fragile and easily reset. Maybe intelligence is not an evolutionary inevitability, but a weird fluke that happens once in a vast span of time. Maybe technological civilizations tend to self-destruct. Or maybe they choose to stay quiet, not because they are afraid of us, but because broadcasting into the universe is like shouting your address into a forest you have not mapped. But here is the pivot that matters for our documentary. The point is not to solve the Fermi paradox. The point is to notice what it reveals about the Milky Way's scale. Our galaxy is large enough that even if it were filled with civilizations, they could still be separated by thousands or tens of thousands of light years, too far for casual conversation, too far for shared culture, too far for a sense of community. The Milky Way can contain a crowded world and still be a lonely place, and that loneliness changes what it means to call the Milky Way home. It suggests that the Milky Way is not just a big container of stars. It is the maximum arena humanity is likely to ever truly influence. We can dream of travelling to other stars, and perhaps our descendants will, over very long times, but the distances between galaxies are so vast that leaving the Milky Way in any meaningful way is likely beyond reach. The local group is a future story for beings with patience measured in millions of years, and even then physics is not generous. So scale does two things at once. It makes the universe look abundant in terms of raw numbers, and it makes the universe look isolating in terms of reach. That is not a contradiction. It is the same fact seen from two angles. And this brings us to the next step, because once you accept how isolated everything is, you start to wonder how we learn the universe's scale at all. How do we measure distances we cannot touch? How do we build a map across billions of light years? What tools turn a sky full of dots into a ladder of depth? That ladder is the reason we can even tell this story. All of this scale talk comes with a dangerous temptation. It can start to sound like we have a perfect cosmic tape measure. Like we can point at Andromeda, point it at a faraway cluster, point at the edge of the observable universe, and read off a clean distance the way you read a street sign. But astronomy is not like that. In astronomy, you almost never measure distance directly. You infer it. You build it step by step. You climb a ladder, one rung at a time, where each rung depends on the one below it. This is why astronomers call it the cosmic distance ladder, because you are always standing on something you measured earlier to reach something farther away. The first rung is the most human one. Parallax. Parallax is the shift in an object's apparent position when you view it from two different locations. You already know this instinctively. Hold up your finger and close one eye, then switch eyes. Your finger seems to jump against the background. That jump is not your finger moving. It is your viewpoint changing. Earth gives astronomers a built-in baseline because we orbit the Sun. As we move around our orbit, nearby stars appear to shift slightly against the far more distant background. Measure that tiny shift carefully, and geometry gives you the distance. For nearby stars, parallax is pure, clean, beautiful physics. The problem is that the shifts get extremely small very quickly. Stars are far, even our nearest neighbours are far. So measuring parallax is hard, and for most of human history it was impossible. Modern space missions change that. When you get above the atmosphere, you remove a huge source of blur and distortion. Suddenly you can measure star positions with astonishing precision, and parallax becomes a powerful foundation. Once you have good distances to nearby stars, you can calibrate the next rung, standard candles. A standard candle is an object whose true brightness is known. If you know how bright something really is, and you see how dim it looks from Earth, you can work out how far away it must be. The trick is finding objects whose intrinsic brightness is predictable. One of the most important standard candles is a class of stars called Cepheid variable stars. They pulse, they get brighter and dimmer in a regular rhythm, and crucially, the period of that pulsing is related to how luminous the star really is. Measure the period and you get the true brightness. Compare that to the apparent brightness, and you get distance. Cepheids are powerful because they are bright enough to be seen in other galaxies, at least relatively nearby galaxies. That is how astronomers began to extend the distance ladder beyond the Milky Way. They used parallax to calibrate nearby Cepheids, then used Cephoids to measure distances to galaxies that contain them. Then comes another rung that is both spectacular and slightly terrifying. Type 1, a supernovae. These are exploding stars that reach a very consistent peak brightness under the right conditions. They are so bright that they can be seen across enormous cosmic distances. When a Type 1 supernova goes off in a faraway galaxy, it becomes a lighthouse visible across a huge fraction of the observable universe. That lets astronomers measure distances on scales where individual stars are too faint to help. At this point, the ladder has carried you from nearby stars to nearby galaxies, to galaxies so distant that their light began travelling toward us billions of years ago. And then, for the truly extreme scales, the ladder blends into something else. Cosmology. Because once you reach great distances, you're not only measuring how far away something is, you're also measuring how the universe has expanded during the time the light was travelling. That means distance becomes tied to the expansion history of the universe. You use redshift, the stretching of light to longer wavelengths, as a clue to how much space has expanded between the source and us. To turn that into a distance, you need a model of expansion. This is why the biggest numbers in this story, like the size of the observable universe, are not measured with a single ruler. They are inferred from a network of observations stitched together with theory. And here is the part that makes science feel honest. Every rung has uncertainty. Parallax has measurement error. Cepheids have scatter and can be affected by dust. Supernovae have variation and require careful correction. Redshift depends on local motions as well as expansion. And the farther you go, the more those uncertainties can compound if you are not careful. So when you hear a clean number like Andromeda at about 2.5 million light years, that is not a magical exactness. It is a best estimate. It comes with a margin of uncertainty. On the scale of a galaxy, that uncertainty can sound huge. On the scale of the universe, it is remarkably precise. The same humility applies to claims about superclusters, walls, and the most distant galaxies. Instruments like the Hubble Space Telescope and the James Webb Space Telescope have pushed our reach deeper into cosmic time, but even their breathtaking images are only as good as the distance framework behind them. You're not just seeing far, you are interpreting far. This is also why astronomy occasionally has moments of tension that sound like drama but are actually health. Different methods sometimes give slightly different values for key quantities like the expansion rate of the universe. When that happens, scientists do not panic, they check the ladder. They check the calibrations, they look for hidden biases. Sometimes the disagreement fades as measurements improve. Sometimes it persists and hints that something in our understanding might need refinement. That is not failure, that is the scientific method doing its job. And it brings us back to the Milky Way in a strangely emotional way. We are inside the system we are trying to measure. We are standing in the forest trying to count the trees. We cannot step outside the universe for a better angle. Everything we know about cosmic scale is built from light that reached us, from careful inference, from patient cross-checking. The numbers are real, but they are not divine. They are human achievements. So when we say the Milky Way is about 100,000 light-years across, when we place it about 26,000 light-years from its centre, when we compare it to Andromeda, to Virgo, to Laniakea, to walls and voids and the observable horizon, we are not reciting a memorized list. We are telling you what a curious species managed to reconstruct from a moving planet around an ordinary star using geometry, physics, and stubbornness. Now we are ready for the final turn, because once you understand the ladder, you understand the real theme of this whole journey. Scale is not only a fact about the universe, it is a fact about perspective. We can be tiny and still measure the enormous. We can be one species in one corner and still draw a map of the cosmos. In the last part, we bring the zoom back home, and we answer the paradox in the only way that actually satisfies. Not by making the Milky Way feel small, and not by pretending it is central, but by showing how it can be both extraordinary and ordinary at the same time. When you have spent hours zooming outward, there is a strange risk. The universe can start to feel like an abstraction, a cold diagram of numbers and distances. The Milky Way becomes a dot, then a grain, then an afterthought in a sea of other grains, and if you're not careful, that can drain the meaning out of the whole journey. So I want to do something simple now. I want to bring you back outside, not to a telescope dome or not to a simulation, just to a dark night, away from city lights, where the sky remembers how to speak to the human nervous system. You look up and you see it, a pale river of light stretching across the darkness. That band is the Milky Way, not as a diagram, as a thing. It is the combined glow of billions of stars too distant to separate with your naked eye. It is the disk of our home galaxy seen from inside, like living in a vast city and looking toward the crowded downtown from the quieter suburbs. Every star you can see on a clear night with your eyes alone is part of this one galaxy. Every familiar constellation, every myth humans ever projected onto the sky, every story told around a fire while someone pointed upward, all of it happened under the ceiling of the Milky Way. For almost all of our history, that ceiling was the universe. Everything beyond it was unknowable. Then, in what amounts to the last heartbeat of human time, we learned what it really is. A spiral galaxy, roughly 100,000 light-years across, holding on the order of hundreds of billions of stars. Our Sun is one of them, sitting not at the centre, but out in the suburbs, about 26,000 light-years from the galaxy's core, in a smaller spiral feature often called the Orion Spur. We are not in the throne room. We are not in the spotlight. We are in a quiet neighbourhood, and that quiet may be exactly why we are here. Because the Milky Way is not just big, it is stable enough, calm enough, and chemically rich enough to build worlds like ours. It is old enough to have forged heavy elements through generations of stars. It is structured enough to provide long stretches of relative safety from the most violent events that happen in crowded cluster cores. Our galaxy is not a paradise everywhere, but it has pockets where life can persist long enough to become complex. So even before we talk about scale, we should admit something. The Milky Way is an extraordinary home. But now we place that home into context, and the paradox arrives again, not as a trick, but as a true description of reality. On one hand, the Milky Way is a giant compared to most galaxies. Most galaxies are dwarfs, smaller, fainter, less massive. If you sampled the universe at random, chances are you would pick something smaller than our galaxy. In that sense, we live in a heavyweight system, a place that towers over much of the galactic population. On the other hand, the Milky Way is one galaxy, among an almost absurd number of galaxies in the observable universe. Even if it is large, it is still one. When you zoom out to the scale of superclusters, filaments, walls and voids, our galaxy becomes a single bead on a long strand. When you zoom out to the scale of the observable universe, it becomes one flicker among trillions. So how can both feelings be true? Because scale is relative. A tall person is tall in a crowd and tiny next to a mountain. A continent is huge to an animal and small to a planet. A planet is massive to a human and invisible next to a star. The Milky Way is the same kind of truth. It is vast enough to humble you and still small enough to be humbled. That is not a flaw. It is the universe teaching you how perspective works. Now here is the deeper turn, the one that makes the whole journey land. The universe may be indifferent, but meaning is not something you find floating out there. Meaning is something that happens. It happens when matter arranges itself into a nervous system that can care. It happens when atoms, forged in ancient stars, become the kind of pattern that can look back at the sky and ask what the sky is. You are part of that pattern. Every atom in your body was made in an earlier generation of stars. Those stars lived, burned and died, enriching space with the heavier elements that make rocky planets possible and chemistry interesting. Over time, that enriched material became the sun and the earth. On Earth, chemistry became biology. Biology became ecosystems. And somewhere inside that long chain, a species appeared that could measure parallax, decode redshift, map walls of galaxies, and argue politely about whether the largest claimed structures are really as large as they sound. That species is us. So yes, the Milky Way is not the centre. It is not the biggest. It is not unique in the way our ancestors once imagined. But it is unique to us in the only way that actually matters. It is where our story happens. It is the only place we have ever lived, and it is likely the only galaxy our descendants will ever truly inhabit, no matter how far we spread among the stars. And that reframes the scale story into something practical. When you realise how isolated galaxies are, you begin to feel how rare a living world might be, even in a universe full of stars. As far as we know, Earth is the only place where life has arisen and become conscious enough to contemplate the cosmos. That might change someday. We might find microbes under ice on distant moons. We might detect biosignatures in the atmosphere of an exoplanet. We might hear a signal, or we might never find anything at all. Either way, the point remains. This small planet is precious, not because it is central, because it is rare, because it is alive, because it is home. Now, one last zoom, and it is a zoom into the future. The Milky Way and Andromeda will likely merge in billions of years. Our galaxy's shape will change, stars will be redistributed, gas will be stirred. The night sky will become a different kind of art. Far beyond that, the expansion of the universe will carry distant galaxies away from us, slipping beyond the horizon, until future astronomers, living in the merge remnant, may look out and see an emptier universe, unaware of the vast cosmic web we now know exists. That is the final irony. Knowledge has a time window. We are living at a moment when the universe is old enough for complex life to exist and young enough that the rest of the cosmos is still visible. We have a view that will not last forever. So when you look up at the Milky Way tonight, hold the paradox gently, because it is the real shape of the truth. The Milky Way is enormous. It is one of the larger galaxies in the universe. It is a grand spiral packed with stars, worlds, and history. And it is also one small light among countless others in a universe so vast that even our biggest words can only point in the right direction. It is our home, and it is not the centre, and both facts make it more beautiful.